welcome back, and let us continue the discussion of this averaged equation in RANS framework. So, we are looking at this average of the product, and this is what we looked at when you take this rho uj averaging and rho ui uj, and we can see there are terms which are containing density fluctuation. So, if you keep those things, that would create trouble. So, the idea is that to avoid these terms. So, that is what we go for density weighted average. So, how you do that? Now, density weighted average, let us say density weighted mean. If we say, then F would be, sometimes we call it also Fabry averaged. Okay. Then the fluctuation relative to density weighted mean would be F double prime, which is F minus F, where we have seen the F, which is ensemble average of this, is in samples summation over 1 to samples Fn. Now, what it allows you, that it allows you that now rho uj, this would become rho uj, and rho ui uj, that will become rho bar ui uj plus ui double prime uj double prime. So, you can avoid the term which will arising like density fluctuations in these terms. So, that is one of the advantage when you have a reacting system. It is a good idea to go for density weighted average, or we call it also Fabry average. Now, we can see these mean properties and the terms. So, the whole idea is that now my governing equation would be again, now based on this Reynolds averaging or Fabry averaging or density weighted averaging, the set of governing equations would be now again transformed. So, once we do that, this is my continuity equation. Now, instead of u bar, this would be u tilde. My momentum equation will get back an extra term which is called the Reynolds stress term, and my scalar transport equation will have one term which is a mean source term. This could be source term due to chemical reaction, this could be anything, and there would be an additional term which is called the turbulent scalar flux. So, these three terms like term 1 Reynolds stress, term 2 turbulent scalar flux, term 3 mean source term. If you look at the complete governing equation, these three terms are not actually closed form. So, we need some sort of an closure approximation for these terms, and this is one of the challenges one encounter while closing this term. Now, we can see and correlate how. So, now when you try to close this Reynolds stress term, this is where you need to invoke your turbulence model. So, your turbulence model will allow you to, so either you can use different kind of RANS model or LES model or whatever it is. So, it is a variant of turbulence model in RANS framework. So, we are not talking about anything on LES, because the equation system would look slightly different. So, that is what we now. So, any RANS based equation like two equation model K epsilon, K omega or RSM, that would close down this, and how, and it will only give rise to your eddy viscosity and all these things that we have already seen as a part of our discussion in turbulence modeling. Now, this is why the importance of turbulence modeling or the discussion on turbulence was required. because now this would be much easier to see when these unclosed terms actually appear in the Governing equation, how we close it. Now, the second term is turbulent scalar flux, so which is written in this fashion. So, typically we use the gradient diffusion assumption, though it is widely acceptable, but only few specific cases this may lead to some spurious results, or one may use second moment closure. Now, the mean source term, that is what is the point of interest, that is the chemical source term. Now, you require all sort of turbulence chemistry interaction model, or one can call it in all range of, this is combustion model. So, you need these models which will allow you to close down that mean source term. So, it could be laminar reaction rate, Eddy-Beckham model, EDC model, flamelet method, PDM method, CMC or MMC. So, this is with the order of increasing expenses in the sense computational expenses, at the same time the complexity also. So, this increases the complexity, so at the same time cost, but at the same time it increases quite a bit of accuracy also. So, all these things increases as you go from top to bottom. Now, the different models which one may like to use for, but we are talking about this kind of combustion. So, the models which are applicable to any mode of combustion could be laminar finite rate kind of model, EDC kind of model, or transported PDF kind of model. So, theoretically, when we look at the theoretical description, these models ideally can be adapted for any kind of mode of combustion, whether it is premixed, non-premixed or partially premixed. Now, there are some models which are applicable to non-premixed regime only, that is mixture fraction or fast chemistry model, flamelet based model, CMC, MMC. These are primarily used for the non-premixed regime, rather they are quite good enough for this regime. When you move to the premix, it requires lot of theoretical modification, and which is applicable to premix zone, that is a flame surface closure model or flame speed closure models, premix flamelet model, G equation models and other models like that. So, there are essentially you try to sort of that capture the flame topology and this. Now, when you say the applicability, that does not mean the accuracy. So, there are subvariants of models applicable to any mode, can be applicable to specific modes only. So, this is what one has to be very careful when talking about these combustion models, because they can be applicable to anywhere, but that does not mean this will provide you accurate results. Now, what we will do now, these are the set of models that one can see. There are simple models, there are statistical based models, transport PDM model, then the models which are very specific to premix combustion, there are models which is specific to non-premix combustion. So, this should give you an idea how we are going to span our discussion around this. Okay. So, first we start with the method of reactive scalars. So, what is that? So, you have an transport equation of any reactive scalars. So, the reactive scalars, they could be species mass fraction, let us say y alpha or yi, and they could be temperature, like that. Now, I can put that thing in a functional form, which is y1, y22, yn and temperature. So, the balance equation where this psi I, which goes for I equals to 1 to n plus 1, because n number of species and then temperature. So, the balance equation would look like del psi I by del t. It is just like another scalar equation, scalar transport equation rather. This is x j, so del of x j rho d I del psi I by del x j plus rho s I, where d I is your mass diffusivity and it could be thermal diffusivity, and then SI is the source term, whether it could be chemical source term or temperature source term. Now, for high Reynolds number, we can neglect the molecular transport. So, that if we neglect, then the gradient transport assumption of the turbulence transport can be used to close this term, like uj double prime. So, this term we can use the gradient hypothesis and we can close this term, where dt would be nu t by Smith number. Then the average transport equation, average transport equation would take the form rho bar del psi I by del t plus, these are obviously when you talk about average, these are all density weighted average or Fabry average, and del psi I by del x j minus del x j rho bar del psi I x j plus rho bar s j. So, again still if you see this term, this is not closed. So, this requires some closing. So, we need to approach like a turbulence models expression for some mean values and something. Now, we can write our heat release. So, the heat release term, one can write that W t rho S t of t, which is rho b T b minus t exponential minus E by R t. Here B is the frequency factor of heat of reaction, T b is the adiabatic flame temperature, and E is the activation energy. Now, we need chemical source term, which has to be also sort of closed or require some modeling, so that we can say that it is a function of temperature. Now, this temperature, which has been widely accepted, we can decompose into two components, T as T fluctuation. So, we can use our Taylor series expansion or Taylor expansion. So, if I use Taylor expansion, then T would be T bar for, let us say, T equals to T plus T double prime, where T double prime is smaller than T prime. So, then we can write S T of this B T b minus T E by R t. Now, the pre-exponential term we can look at Tb minus T at T mean can be written as Tb minus T fluctuation, and exponential term one can write E by RT minus E by R 1 by T square into T minus, so that is at T plus T fluctuation, which would be minus E by RT plus E T fluctuation by T square. So, if I couple these two expressions together, what we get, the final one is that S at T this B Tb minus T exponential E by RT and exponential E by R square. So, that is what it. Now, because of Fabry mean, what we get, that this is equivalent to B Tb minus T tilde exponential minus E by R this. So, which one can write like is T 1 minus T prime Tb minus T E r prime square. Now, the typical value, this term, this T fluctuation by T, that actually lies between 0.1 to 0.3. These are some typical values, but not necessarily it is going to be. This is in the reaction zone of flame. Now, if you have intense fluctuation of the chemical source term around the mean value, this moment method what we are describing here is quite inappropriate due to strong nonlinear effect of the chemical source term. So, if the fluctuations are too high, this is not quite accurate because of this nonlinearity. Now, we can look at these things in, for example, in the isotropic turbulence case. This is how your Fabry averages species transport equation look like. This is the term one has to closed, this is unclosed term, then this is closed like an gradient transport model. If you use a one step global reaction, so this chemical source term can be represented like this, and if it is a decaying isotropic turbulence, then you can write like this. That is just an example. So, here the closure by mean values does not work. So, we have to think about something else. So, now we can look at some of these simple models and see how they are derived. Now, the Eddy Brackham model, it was first, this is something what is used to close the chemical source term for in premix combustion, and it was proposed in 1971 by Spalding. So, you have a inflow, there is a reactant and there is a flame front, then product, then the outflow. So, there are certain assumptions which are sort of associated with this. That is one of the important assumptions is the very first chemistry. So, the combustion process, what it says that the breakup of eddies from the unburned mixture to the smaller mixture, and that means from this side to that side. So, due to this thing, large surface area and duration of this breakup determines the pace. So, that is why this whole terminology came up, that eddy breakup model, because how the eddy breaks up, depending on that the reaction source term are closed. Now, if you look at the average reaction source term for a product, let us say P stands for product, then Wp would be rho constant of EBU epsilon by K y ply fluctuations square root of that. Here this guy is the variance of mass fraction of the product, and this is the eddy breakup model constant. Now, here the two things what happens is the turbulent mixing, sufficiently describes the combustion process. That is number one. Number two, chemical reaction rate is neglected or negligible. So, this is quite simple, but there are issues like if you want to use for, let us say, EGR or lean or rich combustion condition, this is not quite applicable. So, then this model was further developed by Magnussen and 1977, which is called the EDM, eddy dissipation model. So, the first modification was of this eddy breakup model to EDM. Now, what EDM does, that also have certain assumption. So, one of the assumption is that also fast chemistry, that is very fast chemistry, and mixing time which is turbulent. Obviously, turbulent mixing time is the dominant time scale there, So, which means that SI is order of T to the power minus 1, which is epsilon by K. So, that will lead to model my chemical source term, which can be written as A nu I mi epsilon by K minimum of YE nu E me B summation of Yp nu P double prime MP. Here YE, Yp, these are the mass fraction of the reactant. So, mass fraction of reactant and or product, A, B, these are the model parameter. So, these are sort of determined. Now, if you apply to a diffusion flame, for example, let us say diffusion flame, one step chemistry where you write fuel plus you oxidizer to product. So, that kind of one step chemistry if you consider, so you could have, let us say, YF which is greater than YF stoichiometry, then what happens? Y oxidizer would be YF and that will lead to YE is only Y oxidizer. So, my SF would be written as A nu F MF epsilon by K YO by nu O MO, which is A epsilon by K YF stoichiometry. Or the other situation, what could be possible, that YF is less than YF stoichiometric, which will lead that Y is YF. Then my SF I can write A nu F MF epsilon by K YF by nu F prime MF, which is nothing but A epsilon by K YF. Now, if I put some of these issues, so there one can see that it is primarily mixing control phenomena, that is number one, very fast chemistry, and the application, it can be applied to both premixed and non-premixed mode. Now, it connects the turbulent mixing with the chemical reaction, so the rich or lean, whether full or partial conversion, this can be, this does not actually come into consideration. It is simple and robust, that is one of the, but there are certain disadvantages which are quite prominent. So, no effects of chemical non-equilibrium, that is one thing, that means that INO formation, local extinction, this cannot be predicted, extinction. Then also the finite rate chemistry effect are not, finite rate chemistry effects are not considered. So, the fuel consumption is overestimated, that is number one. Then we can have locally high temperature also. So, the finite rate chemistry neglected. So, because of that you can have fuel consumption which is overestimated and locally high temperature. So, these are some of the issues with eddy dissipation model. So, we will look at the other model and how to overcome of this particular issue. So, we will stop here today and continue the discussion in the next lecture.